Hello, so let us solve the problem now. So this function is given to us. This is function from r to the 3 to r. Yes, it is taking three numbers in order and giving us one real number back. So this is a function f from r to the 3 to r. Yes, and now we're supposed to calculate the gradient of this function. Of course, it is better always to equip it with a vector, because you know that the gradient of a function is actually a vector field. So the gradient of the function f calculated at a given point with coordinates x, y, and z is defined to be this vector field. The first component is the partial derivative of f with respect to x calculated at that point. And then the second component is the partial derivative of the function f with respect to y calculated at that point. And similarly, the third component is the partial derivative of that function with respect to z calculated at that point. So let us just calculate each one of them individually. So if I ask you what is the partial f partial x, so I would say that this is equal to, this means that differentiate your function, consider that x is the only variable that you are facing and y and z are considered to be constants. Okay, so here the derivative of 2x squared with respect to x is just simply 4x. The derivative of xy when x is variable and y is fixed is exactly y. Yes? The derivative of y squared when y is considered to be constant, of course, is 0. The same for this one. So that is the answer to the first component of the gradient function, or the gradient vector field. And then I calculate the same thing for the second component. But this time I take y as my variable and x and z constant. So x is constant, its derivative is 0. Z is constant, its derivative is 0. Y is variable. So the derivative of this one when x is constant, y is variable, is just simply x. And the derivative of this one with respect to y is 2y. And finally, partial derivative of f with respect to z calculated at this point. I consider z to be variable and x and y are constants. So if x and y are constants, everything up to here can be considered as one constant. And then of course I have z. So the derivative of this part assumed to be constant is 0. The derivative of z with respect to z is just 1. So this means that the gradient of the function f calculated at that point x, y, and z has three components. The first component is x plus 2y. The second component is actually, the first component is 4x plus y. The second component is x plus 2y. And finally, the last component is the constant number 1. Okay? So this is the first part of the problem. For the second part, we want to find the maximum directional derivative at a given point. So if I want to calculate the directional derivative, so assume that you have a function f. Let me just review a little bit from r3 to r. Then I pick a point in the domain of the definition of the function f, and then I also pick, for example, a unit vector n in the space, and then I can ask what is the direction, what is the directional, or what is the derivative of my function in the direction of the unit vector calculated at the point a, b, and c. So this means, roughly speaking, it means that I stand at this point and then I start moving in the direction specified by this unit vector. In general, my function starts changing, but hopefully you agree, it is intuitively clear, depending in which direction you are moving, the value that you get for the change in the function is different. So when I say that I want to calculate the directional derivative of f at this point with respect to this unit vector. It means that I am standing here, moving in direction of the vector n, and see how fast my function is changing. And then the definition is, of course, the limit of f at that point. So this is the point A, B, and C plus h multiplied by that unit vector minus f of A, B, and C, and then divided by h when h goes to 0. Okay? So that is the definition of the directional derivative, but it can be shown, as it is shown in the course book, Adams, that the directional derivative of the function f at point A and B and C with respect to the unit vector n is equal to the gradient of that function calculated exactly at the same point, but dot product with the unit vector n. So the definition of the directional derivative is as follows, but you can go and refer to the book to see why this is also the case. Now in this problem, in the second part, I want to use this idea. We want to see what is the maximum directional derivative. What is the value of the maximum? So it means that I want to maximize this. Okay? Okay, if I want to maximize this, this is a dot product. By the definition of the dot product, this is equal to the norm of the first vector multiplied by the norm of the second vector, but it is 1 because I'm assuming that n is the unit vector, so I don't write it, multiplied by the cosine theta, which is the angle between this vector and that vector. Okay? So of course it depends, this theta depends on n as well as which point we're looking at the problem. But then it becomes clear, because we know that cosine theta is maximally 1. So if I ask you what is the maximum of directional derivative calculated at this point, you would say that maximizing this quantity means maximizing this quantity. But maximizing this quantity means having cosine theta equals to 1. So then if this is 1, the maximum value is just simply the norm of the gradient function calculated at that point. So here I want to maximize my directional derivative when the point chosen is 1, 1, 1, and 5. So this means that I am more interested in answering this question. So in principle here means I want to fine-tune this unit vector so that I reach to the maximum value for my directional derivative. But according to what we learned here, this is nothing except the norm of the gradient of the function calculated exactly at that point. Yes? Okay, but now if I ask you what is this vector, you can go and use this formula. So in order to calculate this, I need to replace x with 1, y with 1, and z with 5 in this relation. So what do I get? If I replace x and y with 1, this becomes 5, this becomes 3, and this becomes 1. So 5, 3, and 1. So this is nothing except the vector 5, 3, and 1. And I want to find the norm of this vector. So this becomes square root of 5 to the power of 2 plus this to power 2 and plus this power 2. So if you calculate that, it becomes a square root of 35 length units. So that is the maximum possible value for my directional derivatives. Okay? I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.